All right, so today we're going to talk about in a video, basically we're going to kind of go through talking about how many total roots we have, how many are real, and how many are complex. We did talk about imaginary, which is obviously what we're talking about when we're talking about complex roots in our last video. So we're just going to kind of continue to review that and then look at some more examples of the way things are worded and what it's actually talking about to make sure that you understand completely. All right, so looking at this first example, it asks us to tell the total, how many real, how many complex. So remember, we tell how many total roots that we have based off of our degree. So if my degree here for this example is going to be 3. So if my degree is 3, that means I have a total of 3 roots. Okay, so we're going to graph it to determine how many real roots we have. So remember, real roots are where it crosses the x-axis, and we're going to make sure we look for multiplicity. So if it crosses the x-axis, then remember that's got single multiplicity. If it kisses or touches the x-axis, then it's going to have even multiplicity, and if it has a point of inflection, it's going to have odd multiplicity. So I'm going to kind of zoom out, make sure that I don't see anything that's outside of my regular window, and I can see that it crosses the x-axis 3 times. All right, all of those are crossing, so we have single multiplicity on all of those. So we have 3 real roots, which means we have 0 imaginary. Okay. All right, and for number 2. So again, we're looking for the total, which is going to be 4. We're going to graph it, and we're going to look for how many times it crosses the x-axis for our real roots. And I'm zooming out to make sure I don't see anything outside of our window, going back in, and I see that it crosses 2 times. So no multiplicity. So if I have 2 real roots, that means that I have a total of 4, then we're going to have 2 roots left over, but they're not anywhere as far as crossing the x-axis. That means we are going to have 2 imaginary or 2 complex roots. All right, so for our next one, we have a total of 2 roots. Okay, so we're going to look and see how many times it crosses the x-axis. And I'm seeing here that it actually doesn't cross the x-axis at all. So if it doesn't cross the x-axis, we have 0 real roots, which means we're going to have 2 imaginary roots or 2 complex roots. All right, and this one we're going to have 2 roots, 2 total roots, and we're going to continue here. We're going to graph this, and I see that it is going to kiss or touch that x-axis. So that means that it has to have some even multiplicity happening. So if it has even multiplicity, excuse me, then it's going to have to occur at least 2 times. Well, if we only have 2 roots and it has to occur at least 2 times, that's going to be 2 real, 0 complex. All right, so for this one, we have 4 total roots. And out of those 4 total roots, we're going to have how many real roots based off of how many times it touches the x-axis. So I see I have 1, 2 where it crosses, and then I have another root, but it has some even multiplicity because it's kissing or touching the x-axis. So I have 1, 2, and I have to have at least even, so at least 2 more, which we need a total of 4. So we have 4 total, and we have 0 complex. Okay. And for our last example, just telling the total, how many real, how many complex, I have 3 total. So out of my 3 total, I have x to the third minus 2x squared plus x plus 4. And I'm going to zoom out just to make sure. I see that it's crossing that x-axis 1 time. So it's 1 real root because it's got single multiplicity, but I need a total of 3. So I'm going to have 2 imaginary roots as well. All right, so just being able to look at it graphically makes the big difference of being able to tell how many reals, and then whatever's left over is your complex. All right, and looking at number 7, it says a polynomial is given below. Which statement is true about this polynomial? So it has exactly 3 roots, exactly 5 roots. Well, we're still looking at the degree, so the degree is it's going to have exactly 5 roots. So we're going to go ahead and get rid of A and C. So the question is, when it says I have exactly 5 roots that must be real, or I have exactly 5 roots that may be real or complex. So there's no indicator that they must be real. Yes, we can look at it graphically and determine if they're real or not, but there's nothing that we can do to determine by looking at the equation that they must be real. They don't have to be real, but I do have to have a mixture of 5 real and complex. So the fact that it may be real or may be complex, it makes the answer D. All right, so what is the lowest possible degree of the function below? So we kind of did an example like this when we were talking about these in a few videos before where I said the least degree. So if we're talking about the least degree, we're talking about with our multiplicity, even if I have even multiplicity, I'd only use a multiplicity of 2. I wouldn't do 4 or 6. So when I'm looking at this one, I see that it crosses, and then right over here, let's zoom in real good, it crosses 3 times, okay? But right here on this example, this root right here, it kisses it. So if it kisses this axis, that means it's got even multiplicity. And that even multiplicity is only going to have a least degree of, or a least value of 2. So my total is going to be 1, 2, 3, 4, 5. My least degree is 5. And I know, so it says, how do you know? And I put that I know because it's even multiplicity at that problem. Now, what is another possible degree of this function? Well, another possible degree is if instead of it saying that it has even is 2, we could say that even is 4. But that wouldn't be the least degree. But I could say that it has 1, 2, 3, 4, 5, 6, 7 roots. So depending on how much the multiplicity is, depends on the degree of the problem. But the least degree is 5. All right, so it says which pair of values could not be the roots of a quadratic. So quadratic. So remember, quadratic has a degree of 2. So it's saying, given these roots, which one could not be a quadratic? So if I'm looking at this one, these are 2 real roots. So that one can be a quadratic. This would be a multiplicity of 2, so that could be a quadratic. And then I'm looking at my imaginary roots here. So I have 2 minus 3i and 2 plus 3i. So these are conjugates, which means that I could have 2 imaginary roots. So that could also be quadratic. But the difference here is 5. Now remember, imaginary numbers come in sets. So if I have 5i, then it has to have another root, which is negative 5i. If I have 3 minus 5i, then I have to have another set that's 3 plus 5i. So D could not be a quadratic because D would have a degree of 4. Okay, so when I'm looking at this one, this for D, it would have to have a degree of 4, where the others would have a degree of 2. So this one is not a quadratic. That would actually be a degree of 4 or a quartic polynomial. Okay. All right, so number 10, reducible and irreducible. So reducible basically just means factorable. Can I factor the problem? Irreducible means that it's not factorable. So I have this polynomial, this quadratic, and they want me to determine, is it reducible or irreducible? Does it have 2 distinct real roots or 2 distinct complex roots? So the first thing I'm going to do is I'm going to look at it graphically. And I see that when I have this, I see that I have 2 distinct real roots. I have a real root at these 2 values. So I can go ahead and get rid of C and D because those are not complex, those are real. So the question is it reducible or not reducible? Is it factorable, not factorable? So how do I know if it's factorable? Well, this is a trinomial, so I would do my t-chart or x-chart, and I need to know, do I have two numbers that multiply to give me -7, but add to give me 2? So really the only options would be 1 and 7, and there's no way 1 and 7 can work to give me 2. So this is not factorable. And if it's not factorable, then it's irreducible. So the answer is B. Another way to tell is my decimals here for these problems. As I kind of zoom in, I should be able to see like 1.82. That's going to probably wind up being an irrational number. And because the irrational number, that means it's not factorable. Factorable problems are going to have rational numbers. And remember, rational numbers like whole numbers are things that can be turned into fractions. Whew. All right, so number 11. A polynomial has a lead coefficient, so the number in front of everything is 1, and has at least 3 distinct zeros. Now, we don't know what the degree is because it says that it has 3 distinct zeros, but it could have some complex in there. We just know that when we factor it, it should have a factor at -4, multiplicity 1, a factor at -2, multiplicity 1, and a factor at 1 and multiplicity 2. Well, if I have 1, 1, and 2, that means I should have a least degree of 4. Well, if I look at these, I can get rid of A and B. Those are least degrees of 3. So I'm going to just graph them at this point. All right, so when I look, I have one root at 4, which this one says that it had one root at -4. So C is not going to work. So let's change up the values and regraph this. And I have even multiplicity at 1, that's true. I have single multiplicity at -2, that's true. And I have single multiplicity at -4, so the answer is D. All right, so for this one it says the graph given, and it has a 0 at -2. What are the other roots? So again, if I look at this problem, I have y equals x to the third. I have 2x squared minus 5x plus 10. Now, there's a little bit more going on here because that point was a little bit thicker than normal. So I have a root at -2.236, which is going to be an irrational root of some sort. And if I zoom in, I have a root at 2, which we already know. There's a root at 2. And we have another one at +2.236. So what I need to do is I need to figure out what are the other two roots. Well, they gave them to me in the quadratic formula is where they developed these. And that means that you would have to do synthetic division, reduce it down, plug in the quadratic formula. Or I could just check my answer choices. Obviously, I don't have -5 and 5. I have 1 minus the square root of 5. 1 minus the square root of 5 does not give me the value that I'm looking for. So then we have negative square root of 5. That does give me one of my answers. So I have the square root of 5 positive. So that one's going to be our correct answer for our 2 pieces left over. Okay. All right, so number 13, which statement about the zeros, so zeros are the x-intercepts of this cubic function. So cubic function or cubic polynomial means a degree of 3. So there must be one complex zero, not just real zeros. Well, we can't determine that. We don't have an equation. We can't graph it. All I know is I have 3 zeros. I know that I could have a mixture of complex. I could have a mixture of real. So that is not a true statement. I don't know. B, if it is a cubic polynomial and it has 3 zeros, then it must have at least one complex. Well, it can't have at least one complex because complex comes in sets. Imaginary numbers come in sets, so I would have to have at least 2. That doesn't work. And like I said, I don't have to have complex at all. I could have just real. I could have one real and two complex, so that doesn't work. If I have a polynomial that's cubic, then it has a maximum of 3 zeros. Well, that is true because if I have a cubic function, that means its degree is 3. So I have a maximum of 3 zeros. That is a true statement. The other one then said if I have -4 and 3, there must also be a complex. Well, that's not true because if I have -4 and 3 and I have a complex, then I would have to have two complex, which would make it a degree of 4. All right, so what does this say here? This basically is saying that x equals -3 and x equals -1. If that equals 0, then these are zeros. Okay, so they're asking me which one of those answers gives me that. So at this point, I'm just going to graph them all, and I'm going to look. So this one has 5, 3, and +1. So these are not inside of the polynomial. These are saying that x is equal to -3, x is equal to -1. So A doesn't work. All right, so my next one. All right, so I'm looking here. I have a 0 at -3, so that is true. I have a 0 at -1. That is also true. I don't have any more zeros here because there's multiplicity. So therefore, the answer for that one is B. All right, so really the last problems that we went over, they weren't hard problems. They were just the way some of it was worded. I wanted to make sure that you had some exposure to some of the wording there. If you have any questions, let me know.